Hi everyone and welcome to my channel. Today we'll be doing structure of atom. So in the previous chapter we learned that atoms are the fundamental building blocks of matter. So during the 19th century, the challenge for scientists was to understand the structure of atom and to explain its properties. So many experiments were carried out for this. We'll just go through all these experiments one by one. So first in 1886, okay, E. Goldstein discovered the presence of positively charged rays in a gas discharge. Okay, he found positively charged rays and he named these rays, okay, these positively charged rays as anode rays or canal rays. Okay, but he didn't have any clear idea of why they existed or any properties of them other than that they were positively charged. It was Rutherford who correctly identified their existence and named them protons. We'll come to that experiment later. So Goldstein found the presence of positively charged rays and he named them as anode and canal rays. But the discovery of positively charged rays in that experiment led to the failure of Dalton's atomic theory. We have learned in the previous chapter that Dalton said that atoms are indivisible and indestructible, right? But the discovery of positively charged rays in the perforated glass tube led to the failure of Dalton's atomic theory, because if atoms were indivisible, there wouldn't be any subatomic particles, that is these positively charged rays wouldn't be found. So it led to the failure of Dalton's atomic theory. Later on in the 1900s, J.J. Thomson came up with an experiment and proposed a model for the structure of atom. It was J.J. Thomson who found the presence of electrons. J.J. Thomson, he found the presence of electrons. Okay, so his uh, discovery was that we'll imagine atom as a cut watermelon piece, that is a round watermelon piece. Okay, he said that the red flesh was the positive and the black seeds, okay, they were the electrons embedded on them. Red flesh were positive charges and the seeds embedded on them were negative charges. So the two conclusions that he made from his experiment were that atoms consist of positively charged sphere, okay, atoms consist of positively charged sphere and electrons are embedded on it. Okay. The second conclusion he made was that the positive and negative charges are equal in magnitude. So the whole atom as a whole is electrically neutral. Electrically neutral. So this is what he concluded from his experiment. He said that atoms, in an atom, the positive charged sphere and the electrons are embedded on it, and the positive and the negative charges are equal, and the atom as a whole is electrically neutral. Now we'll see the Rutherford's model of atom. Rutherford conducted the famous gold foil experiment. Okay, Rutherford's model of atom. He conducted the very famous gold foil experiment. Let's see the experiment, how the experiment set up. So there was a alpha beam generator. Okay, this is where the alpha beam was generated. Okay, and he placed a very thin gold foil. It was so thin that it was only 1000 uh, atoms thick. Okay, only 1000 atoms thick. Even Rutherford compared this gold foil as a tissue paper. So it was that thin, 1000 atoms thick. It was a gold foil. Okay, and then there was this screen. This screen. The screen is this big. Okay. So this was the setup. This is the alpha beam generator, okay, where the alpha beams are bombarded, and this is the gold foil, and there was this detector. Okay, so what are alpha beams? Alpha beams are doubly charged helium ions. They are doubly charged helium ions. So they are positively charged. Okay, that is, it's helium 2 plus, so it's positive in charge. We have to note that it's positive charge. Rutherford found that most of these alpha particles went straight through the gold foil. Okay, it just went straight through the gold foil. There wasn't any difference at all. Very few particles were deflected in small angles. Okay, they were deflected in small angles, very few. And then the third observation he made, that very small fraction, that is 1 out of 12,000. Okay, 1 out of 12,000 particles rebound, that is, took a U-turn, came back, bounced back. Okay, so there were three observations. One was that most of the particles went straight. Okay, there wasn't any difference at all. The second one was that some particles were deflected in small angles. And third, 1 out of 12,000 rebound back. Okay, he was really surprised with the third observation. So the conclusion he made from these observations was that since most of the alpha particles passed straight, most of the space inside the atom is empty. Most space inside the atom is empty. So deflected in small angles means that positive charge occupies very little space. The last observation was the very important one. The very small fraction, that is 1 out of 12,000 alpha particles rebound back, indicating that all positive charge and the mass of the gold atom were concentrated in a very small volume within the atom. That is, the positive charge and mass were concentrated inside the atom in a very small volume. So from the observation of his experiments, Rutherford came to a conclusion and explained the structure of atom as that there is a positive charged center called nucleus. Okay, so he said that there is a positive charge center called the nucleus, and all mass resides inside the nucleus. Okay, so there is a positive charge center and it's called the nucleus, and all the mass resides inside the nucleus. The electrons, he also said that electrons revolve around the nucleus. The electrons revolve around the nucleus in well-defined orbits. Okay, so the electrons revolve around the nucleus in orbits. The size of the nucleus, size of the nucleus is very small as compared to the size size of the atom. We know the size of the atom is very, very, very small. We can never see it with our naked eyes. So the size of the nucleus is even small compared to the size of the atom. The drawback of his experiment was that he couldn't explain the stability of the atom. That is, orbital revolution of electron is not stable. Any particle in circular motion would undergo acceleration and thus radiate energy. So the electron would, as it moves around the orbit, it would lose its energy and ultimately fall onto the nucleus. Okay, but we know that atoms are stable. So he couldn't explain the stability of the atom. That was the drawback of his experiment. Later, Niels Bohr came up with the model of an atom which is considered accurate till date. So he explained the stability of the Rutherford's experiment. Okay, he said that only certain special orbits, okay, Niels Bohr's experiment, he said that only certain special orbits known as discrete orbits of electrons are allowed inside the atom. Okay, and when the electrons are revolving around in these discrete orbits, the electrons do not radiate energy. So he explained the only drawback of Rutherford's experiment, and he said that there are special orbits. Okay, the special orbits called as discrete orbits. Discrete orbits, they are also called as shells. Okay, the electrons revolve around in these special orbits. So when the electrons revolve around in these discrete orbits, the electrons do not radiate energy. Okay, so the stability of the atom was thus explained. So let's see how it is. So inside an atom, this is the nucleus. Okay, the positive charge and the mass of the atom resides in this, and then there are these discrete orbits or the shells. Okay, suppose these are these discrete orbits. They have special names. That is, if this is K, this is L, this is M, so on. Okay, or they can be also called as, see, if K is equal to N is equal to 1, this is N is equal to 2, this is N is equal to 3, so on. So this is how they are named, and these are the discrete orbits or the discrete shells. We'll see in detail how electrons are placed in these shells, what is the maximum number of electrons occupied in a shell and all. And it was further later that a scientist called J. Chadwick led to the discovery of another subatomic particle inside the atom, and that was named neutron. Okay, so he said that this has no charge, it has no charge, it is chargeless, and it has a mass equal to that of the proton, mass equal to proton. He also said that this was placed inside the nucleus. It is found inside the nucleus of an atom. So it is J. Chadwick who found the presence of neutrons. So let's just wrap up. So we have learned that atom has 3 subatomic particles. Okay, that is, there are 3 particles inside an atom. That is electrons, protons and neutrons. Okay, so electrons are negatively charged, protons are positively charged, and neutrons have no charge. So if you're getting confused on how to learn these, okay, see, positively charged means positive. Okay, see, P, positive and protons. So PP, so they go together. Neutrons is N, no charges N, right? So they go together. So what is left will be negatively charged, that is electrons, right? Okay, this can be written as E minus, they can be written as P plus, and this is written as N. Okay, now the electrons revolve around the nucleus. Okay, the electrons revolve around the nucleus, they form, the protons and the neutrons are found inside the nucleus. Okay, they form up the nucleus, that is the middle of the atom. Okay, the protons have mass 2000 times more than that of electrons. Okay, so this is 1 by 2000 mass of protons, and they have 2000 times mass of the electrons. Okay, so Bohr had said that electrons are found inside the orbits around the nucleus. Okay, so how are these electrons distributed in these shells? So Bohr and Bury, they are two scientists, they came up with three rules how electrons are filled inside the in these orbits. So the first rule they had said was that the maximum electrons found in an orbit in this shell is 2n square, where n is the number of the orbit, that is n is equal to 1, n is equal to 2, n is equal to 3, so far. So the maximum number of electrons found in the K shell will start from n is equal to 1. So maximum electrons in K shell, that is n is equal to 1, will be 2n, that is n is equal to 1 square, that is equal to 2. Okay, so the maximum electrons in L shell, that is n is equal to 2, is equal to 2 times 2 square, that is equal to 2 times 4 is equal to 8. Third one is in M shell, that is n is equal to 3, that is equal to 2 times n square, right? Maximum electrons is 2n square. So that is 2 times n is 3 square. 3 3s are 9, 9 2s are 18. Fourth one for n shell, that is equal, n is equal to 4, 2 times 4 square, that is equal to 4 4s are 16, 16 times 2 is equal to 32, so on. So the first rule was that the maximum electrons in any orbit is equal to 2n square. Okay, the second rule was that the maximum number of electrons that is found in the outermost shell is 8. Okay, if in an atom it is the outermost shell, it can only occupy 8, it can't occupy more than 8 electrons. Okay, so the maximum number of electrons, in outermost shell is 8. Okay, and the third rule was that electrons are filled in stepwise manner, that is, it is not filled randomly. First, see, the first orbit is 2 electrons. Okay, the maximum electrons is 2. So first, the first orbit will be filled, that is K orbit will be filled with 2 electrons, and then only it will go to the L shell. L shell will first fill 8 electrons and then only go to the M shell. Okay, so it is filled in stepwise manner. In the textbook, the schematic diagram of the first 18 elements are given. So we'll see them. See, let's see the first element, that is hydrogen. Okay, it has only 1 electron, so 1. Then helium. So this is the nucleus. This is the nucleus of the atom. Then the orbit. Okay, helium. Helium has 2 electrons. So see, 2. So the next one is beryllium. Okay, so this is the nucleus. So the maximum electrons that can be fit in the first shell is 2n square, that is equal to 2 times is equal to 2. So after the 2 electrons are filled, the next electron will go to the second shell. Okay, so beryllium has 2 shells, so it will be here, third one. So on. So in this shell, that is 2n square, in the second shell 8 electrons can be filled. So it will go on till till 8 electrons are filled. This shell will fill 8 electrons and then only go to the next shell. So this is the schematic diagram of neon with atomic number 10. That is 2 electrons are filled in the first orbit and 8 electrons are filled in the second orbit. Okay. So let's see the next element, that is sodium with atomic number 11. Okay. So this is the nucleus and there are 2 electrons in the first orbit, and then in the second orbit we have 8 electrons. Okay, because the second orbit can fill up to 8 electrons, 1 2 3 4 5 6 7 8. So still we have 8 9 10, we have one more electron to be filled. So this electron is filled in the third shell. So this is the stepwise manner, that is the electrons are filled in the stepwise manner. Now we'll see about valency. So the electrons present in the outermost shell is called as the valence electrons. Okay, the electrons present in the outermost shell is called the valence electrons. Valence electrons. So Bohr and Bury said that the outermost shell, the maximum number of electrons is 8. Okay, so these elements which had 8 filled electrons in the outermost shell, they were called as the inert elements. They were seen to be less reactive. Okay, that is the elements which had the outermost shell with filled 8 electrons, they were seen to be less reactive and they were called octet. Okay, so the elements which had 8 electrons filled in the outermost shell, they were called as octet elements. Okay, and these octet elements were also found to be less reactive. So it was concluded from this observation that all the elements that react with the same element or different elements was to gain this valency, that is to get fully filled outermost shell. Okay, so actually atoms react to be octet elements. So atoms react to be octet. Okay, this can be either by sharing electrons, losing electrons, or it can be also either by gaining electrons. Either way, they just want to be octet. That is, they need fully filled outermost shell. To be very clear, if the number of electrons in the outermost shell is 4 or less than 4, okay, if it is 4 or less than 4, it is easier to lose these electrons, okay, because the number is small. It's easier to lose these electrons. So the valency can be said as the number of electrons in the outermost shell. Valency is the number of electrons in the outermost shell. If suppose there are 3 electrons in the outermost shell, it is easier to lose these 3 electrons to gain octet. So the valency will be 3. Okay, this will be the valency. But if there are 5 or more than 5, okay, it is easier to gain because losing so much electrons is very difficult. 5 or more, it will be very difficult to lose these electrons. So it is easier to gain the required number of electrons. If suppose we have 6 electrons in the outermost shell, we need 2 more to gain 8 electrons. So so we need 2 electrons to gain octet. So it is easier to get these 2 electrons rather than losing 6 electrons, right? So here valency will be equal to 8 minus 6, that is 2 electrons. So here in the first case, we are losing a certain number of electrons, that is if it is 4 or less than 4, we are losing electrons. So that much electrons which we are losing, that is from the outermost shell which we are cancelling totally, will be the valency. So that we get octet. Here in this case, when 5 or more than 5 are there, the number of electrons which we gain, the number of electrons, that is will be the valency. Suppose there are 6 electrons and we need 2 more electrons to require to get octet. So that 2, that extra number of electrons which we got will be the valency. Okay. Let's consider lithium. Lithium has atomic number 3. Okay, so it's got this nucleus, and the first orbit it has 2 electrons, and in the second orbit it has 1 electron. Okay, so here in this case of lithium, the second orbit we need 8. Okay, so the outermost is 8. So here in this case, it is easier to lose this 1 electron than to gain 8 electrons. I mean 7 electrons to require. So it is easier to lose this 1 electron, okay, and then gaining 7 electrons, right? So here lithium will lose 1 electron to gain octet. So this valency is, its valency is 1. Valency is 1. Let's consider fluorine. Its atomic number is 9. So this is the nucleus. In the first it has 2 electrons. So the rest will be 7. 1, 3, 4. Yeah, 7. So 1, 2, 3, 4, 5, 6, 3, 4, 5, 6, 7, 8, 9. So in the outermost shell it has 1, 2, 3, 4, 5, 6, 7. It requires one more electron to gain octets. Okay, one more electron. So it will be easier for it to accept 1 electron than losing 7 electrons, right? It is easier for it to receive 1 electron than losing all these 7 electrons. So here in this case the valency is calculated as 1. That is, the extra amount of electron we are gaining is called the valency. So the valency is the combining capacity of an atom. It is called the combining capacity of an atom. That is the number of electrons it's either gaining or losing to get octet. Okay, so the extra amount of either the electron or the number of electrons which we are losing from its orbit is called the valency. Now moving on to atomic number. Atomic number is the number of protons. Okay, the number of protons is called the atomic number. The number of protons present in the nucleus of an atom is, and it is denoted by the letter Z. For example, let's say carbon. Carbon's atomic number Z is equal to 6. That is, the number of protons in carbon is 6. Now let's see mass number. Mass number of an atom is the mass concentrated in the nucleus of an atom. Okay, and in the nucleus we have protons and neutrons. So mass number is equal to number of protons plus number of neutrons. Mass of an atom is concentrated in the nucleus. So mass number is equal to the number of protons plus number of neutrons, that is the subatomic particles found in the nucleus of an atom. So for example, let's see the carbon itself. Mass number of carbon is equal to 6 plus 6, that is equal to 12. This can be represented in an element as, write the element, so we are considering the carbon itself, the mass number first, okay, on top, and the atomic number. So we write element, mass number and atomic number here. Okay, so this is how we represent an element. Okay, so how to remember this is the bigger number, that is the mass, on top, and the smaller number bottom, that is atomic number. Moving on to isotopes, they are the same elements having same atomic number but different mass number. So what you have to keep in mind is that they are same elements, okay. So they have the same atomic number but different mass numbers, okay. So for example, the isotopes of hydrogen, okay, let's say the isotopes of hydrogen are protium, deuterium and tritium, okay. So here protium can be written as H, they have the same atomic number, so that is 1. For protium, the mass number, the mass numbers differ, so it is 1. So deuterium, it is H, the atomic number is same 1, the mass number differs, that is 2. And for tritium, it is H, the atomic number is same, the mass number is 3, okay. Another example of this is carbon. There is carbon, the atomic number is same, okay, the mass numbers become 12 and 14, okay. And we have one more, that is chlorine, the atomic number is same for it, that is 17, but the mass numbers are 35 and 37. So in isotopes, they are the same elements, they have the same atomic number, but different mass numbers, okay. So this is what you have to keep in mind, they are the same element, isotopes are same elements having the same atomic number but different mass numbers. So since they are the same elements, their chemical properties are same, but physical properties are different because the mass numbers differ, okay. The chemical properties are same. So let's see the applications of isotopes. The first one is uranium, okay. The different isotopes of uranium are used in nuclear reactors, okay. They used in nuclear reactors. The second one, cobalt. The different isotopes of cobalt are used in treatment of cancer. And third one is iodine, okay. The different isotopes of iodine is used in the treatment of goiter. Goiter is that disease which affects the neck, the neck swallows, it's the deficiency of iodine. So it's used in treatment of goiter. For exams, it can be asked, what is isotopes? Explain isotopes, give few examples and explain their applications. Now we'll see what is isobar. Isobar are different elements, okay. They are totally different elements. They have different, so since they are different elements, they'll have different atomic number, okay, but they have same mass number, okay. They are called as isobars, okay. They are called as isobars. So example will be calcium and argon, okay. They have totally different atomic number because they are different elements, right. So their atomic numbers are 20 and 18, okay, but their mass numbers are 40 and 40.